Good morning, good afternoon, and good evening. This video will discuss the lesson 1 of STM 112, limit of a function. Before we start, we will go through quickly the definition of the different terms in this lesson, and then we will proceed to the guided practices. Let's begin with the definition of limits. Consider a function f of single variable x. Consider a constant c, which the variable x will approach. C may or may not be in the domain of f. The limit, to be denoted by L, is the unique real value that f of x will approach as x approaches c. In symbols, we write and read this process as the limit of f of x as x approaches c is L. The existence of a limit of a function f as x approaches a constant value c is dependent on the one-sided limits where x approaches from the left of c and where x approaches from the right of c. In mathematical form, it would look something like this. So for a function to have a limit, it has to have two equal one-sided limits. If they are not equal, then the limit of that function does not exist. When dealing with f of x as a rational function, we may conclude that the limit of that function is either positive or negative infinity if x approaches to a certain value of c that makes the numerator a non-zero and the denominator 0 when evaluated. Next are the basic limit laws. For the constant law, it's very basic. The limit of k as x approaches to c is k. K being a constant value. For example, the limit of negative 3.36 as x approaches to 2 is just negative 3.36. So we basically have to copy the constant value. The limit of 69 as x approaches to 1 is 69. The limit of the identity function law. In this law, we simply have to copy the value of c if we are trying to find the limit of just the variable x. So for the examples, the limit of x as x approaches to 6 is equal to 6. The limit of x as x approaches to negative 12.5 is negative 12.5. For the constant multiple law, the limit of k times f of x as x approaches to c is equal to k times the limit of f of x as x approaches to c. So basically, we just moved the k, and then we find the limit of f of x. For the examples, the limit of 12x as x approaches to 3. So here we move the 12 and then find the limit of x. And then from there, we use the limit of the identity function law and to get 3. So 12 times 3, that's just 36. Next, the limit of 0.2x as x approaches 6. So again, we move 0.2, find the limit of x as x approaches to 6, and then eventually we will get 1.2. For the sum and difference law, we basically have to separate the different functions or the terms involved. So the limit of f of x plus or minus g of x as x approaches to c is equal to the limit of f of x as x approaches to c plus or minus the limit of g of x as x approaches to c. So for the examples, the limit of x minus 2 as x approaches to 4 is equal to the limit of x as x approaches to 4 minus the limit of 2 as x approaches to 4. So we use the limit of the identity function to get the values of 4 and 2. So 4 minus 2, that's just 2. Next, the limit of 2x minus 3 as x approaches to 1. So here we can use the constant multiple law to move the 2, and then we find the limit of x as x approaches to 1 minus the limit of 3. So we have to evaluate, and then eventually we'll get to our answer, which is negative 1. For the multiplication and division law, it's very similar to the sum and difference law, in which we just have to separate them. The limit of f of x times g of x as x approaches to c is equal to the limit of f of x as x approaches to c times the limit of g of x as x approaches to c. So for example, the limit of x times x plus 1 as x approaches to 1 is equal to the limit of x as x approaches to 1 times the limit of x as x approaches to 1 plus the limit of 1, and so on. So using the other limit laws that we learned, we will get 1 times 1 plus 1, which will give us 2. Next, the limit of 2x plus 3 times x plus 2 as x approaches to 1. So we separate them. We find their individual limits. So the limit of 2x plus the limit of 3 times the limit of x plus the limit of 2, all as x approaches to 1. Eventually, if we use the limit laws and we will evaluate them, we will get 2 times 1 plus 3 times 1 plus 2, which will give us 8. Next, the division law. The limit of f of x over g of x, or divided by g of x as x approaches to c, is equal to the limit of f of x as x approaches to c over the limit of g of x as x approaches to c. So we have to remember that in division, we can't have a 0 for the denominator because it would give us because the function will be undefined, and we don't want that. So for the examples, the limit of x divided by x plus 4 as x approaches to 2 is equal to the limit of x as x approaches to 2 over the limit of x as x approaches to 2 plus the limit of 4, and so on. Again, so using the other limit laws, we will get the values of 2 over 2 plus 4, which will give us 1 over 3. Next, the limit of x minus 3 over x plus 1 as x approaches to 2. So the limit, it is actually equal to the limit of x minus the limit of 3 over the limit of x plus the limit of 1, all as x approaches to 2. So again, we have to keep in mind that we have to keep on using the limit laws. So here we can use the limit of identity function. So the limit of x as x approaches to 2 is just 2. And then we'll use the constant law. The limit of 3 as x approaches to 2 is just 3. So we can also use those law in the denominator to get 2 plus 1. And then eventually we will get negative 1 over 3. For the power law, the limit of f of x raised to the power of p as x approaches to c is equal to the limit of f of x as x approaches to c raised to the power of p. The root law and power law are similar in such a way that we have to find first the limit of the function before we apply the power or we find the root. So for the examples of the power law, the limit of x squared as x approaches to 5. So we first have to determine the limit of x as x approaches to 5, and then lastly um, we include the power. So the limit of x as x approaches to 5 is just 5, and 5 raised to the power of 2 is 25. Next, the limit of x minus 3 raised to the power of 3 as x approaches to 1. So here, we have to find first whatever's inside the parentheses. So the limit of x as x approaches to 1 minus the limit of 3 as x approaches to 1. Once we get their limits, which are 1 and 3, and then we do the operation 1 minus 3, that is negative 2, raised to the power of 3 is just negative 8. For the examples of root law, the limit of the square root of 8x as x approaches to 2. So again, we just simply have to find the limit first of the function before we actually um, include the roots or we find the root. So we have to find the limit of 8x. So we can use the constant multiple law to move the 8, and then we are left with x. So we find the limit of x as x approaches to 2, which is just 2. So now we have the square root of 8 times 2. 8 times 2 is 16, and the square root of 16 is just 4. Next, the limit of the cube root of 2x plus 2 as x approaches to 1. Again, we will have to use or include the roots or to find the root of the limit at the end. We have to first find the limits of whatever's inside the radical sign. So 2x, that's basically 2 times the limit of x as x approaches to 1 plus the limit of 2 as x approaches to 1. So we will get 2 times 1 plus 2. And then eventually we will get the cube root of 4. Now, finally, we will try to answer the guided practices. So for the first function, the limit of 12x squared minus 3x plus 8 as x approaches to 2. So just from looking at the problem or the function, we can already decide what's our first step, which is to separate them using the sum and difference law. Also, we can already apply other laws, including the constant multiple law, and eventually we will also use the constant law for the limit of 8. But first, let's discuss what we have done here. So from 12x squared, we move the 12, and then we save the power for last, and then we just have to find now the limit of x as x approaches to 2. Same goes for 3x. We move the 3 and we find the limit of x as x approaches to 2. And then lastly, we find the limit of 8 as x approaches to 2. So from there, we try to evaluate, we try to answer um, the limit of x as x approaches to 2. So that's basically 2 raised to the power of 2. So that's 2 times 2, which is 4. Next, the limit of x as x approaches to 2 is again just 2. And lastly, for the limit of 8, you can just use a constant law to determine that the limit is 8. So 12 times 4 minus 3 times 2 plus 8 is 50. Next, we have the limit of 4t plus 6 over t squared plus 1. So we can use the division law to separate them. So we have to individually find the limits first of the numerator and the denominator. So for the 4t, we can use the constant multiple law to move the 4. Now we are left with the limit of t as t approaches to negative 3, plus the limit of 6 as t approaches to negative 3, and then over the limit of t as t approaches to negative 3 raised to the power of 2, plus the limit of t, the limit of 1 as t approaches to negative 3. From there, we can use the limit laws to determine the values. So we get 4 times negative 3 plus 6 over negative 3 squared or raised to the power of 2 plus 1 to get negative 3 over 5. Now, for the limit of x squared minus 25 over x squared plus 2x minus 15 as x approaches to negative 5. Before anything else, we'll have to simplify first the function. We can do that by factoring out or by transforming them into binomials. So we can cancel x plus 5. So if we do that, we are just left with x minus 5 over x minus 3. From there, we'll apply all the limit laws. So it becomes the limit of x as x approaches to negative 5 minus the limit of 5 as x approaches to negative 5 over the limit of x as x approaches to negative 5 minus the limit of 3, so on. So from there, we'll get negative 5 minus negative 5 over negative 5 minus 3 to get 5 over 4. Next, the limit of 2z squared minus 17z plus 8 over negative z plus 8 as z approaches to 8. So in this kind of functions, we have to simplify them first by factoring or transforming them into binomials, like the previous function. So from here, we can cancel out z minus 8 and the z minus 8. So we cancel them out. We are just left with 2z minus 1 and then over negative 1. From there, we'll apply the limit laws. So we get 2 times the limit of z as z approaches 8 minus the limit of 1 as z approaches 8. Over the limit of negative 1, since this negative sign can mean that there's a 1, the value of 1 here. So we'll just use that to visualize and use our the limit clause. So again, over the limit of -1 as z approaches to 8. And then we will get these values. So the limit of z as z approaches to 8 is just 8. So 2 times 8 minus 1 over -1 is just negative 15. 2 times 8, that's 16, minus 1, that's positive 15, times -1, it becomes negative 15. Lastly, we have the limit of x over the negative uh, of square root of x plus 9 plus 3 as x approaches to 0. So here, since we have a square root, we have to radicalize the expression first. So we basically have to multiply the conjugate of 3 minus the square root of x plus 9. Oh, by the way, we use the commutative property to move the positive 3 in front for our convenience. And then we're able to find the conjugate, which is 3 plus the square root of x plus 9. So if we radicalize the expression, we will get x times 3 plus the square root of x plus 9 over 9 minus x plus 9. Now, we can distribute the negative sign to positive x plus 9, which will become negative x and negative 9. So our function or our values in our denominator will be 9 minus x minus 9. Here we can cancel out 9 since 9 minus 9 is already 0. So we are left with negative x. So from there we can just cancel x and x together. So we are just left with negative 3. By the way, the negative sign comes from the denominator or the -1 in our denominator. So negative 3 minus the square root of x plus 9. So basically this. Now, we can now apply we can apply the limit laws to find the limit. So we begin with using the sum and difference law. So we find the limit of -3 as x approaches to 0 minus the square root of the limit of x as x approaches to 0 plus the limit of 9 and so on. So if you try to find the answer, we will get the values of -3 minus the square root of 0 plus 9, which will give us -3 minus 3, which is just -6. Now, these are the table of values of the previous functions that we evaluated. In this kind of table, I made this kind of table to be the combination of for the both one-sided limits from the left and from the right. And I did not include that many values for C since that would make the work lengthy. So instead, I want it to be quick but accurate nonetheless. So I just get, so for example, in the limit of 12x squared minus 3x plus 8 as x approaches to 2, I simply get the closest value to 2 from the left, which is 1.99999999, and the closest value to 2 from the right, which is 2.000000001. And then we simply have to replace these values to x to get the values of f when we try to evaluate using these values. So if we use 1.99999 so on, we get for 49.99955, which is close to 50 or is approaching to 50. And when we use 2, we will actually get exactly 50. For the 2.000001, we get 50.000045, which is approaching to 2, but from the right side. So since from the values that we got, we can determine that both one-sided limits approaches to 50. So if they are the same, that means the limit of this function does exist and is 50. So you could stop this video and look at the table of values and compare them to your own work. When you do the table of values for the previous functions, you can check if we have the same answer or we don't. By the way, it is not required that you have a certain value, certain number of digits after the decimal point. You just have to get you just have to use certain number of digits after the decimal point that will give you an answer to where it is approaching. For example, some values may only require you to use 4 digits, and some may really need you to use like 8 or maybe more. But there's no exact number that you should be using. It's up to you. For the next set, uh, we have this. And then lastly, we'll try to find the limits using the graphs. So for the limit of f of x as x approaches to -5 from the right, since we have a plus sign here from the right, first, when dealing with graphs, we just have to find first the point of c or the value of c, which is -5. So determine where is -5, which is around here, and find the graph or the line, which is this. It touches -5 at 2. So that means the limit for this function is 2. Next, for the limit of f of x as x approaches to -2 from the left. So -2. Where is -2? -2 is around here. And the line or the graph that touches -2 is this. So from the left of -2, so going here, so we'll end up at -1. So the limit of this function is actually -1. Next, the limit of f of x as x approaches to 3. So we'll have to find +3, which is around here. So notice that it's not a one-sided limit. That means we have to find the one-sided limits first. So from the left, we have here going to from the left to +3. And we'll end up actually on +2. Now from the right, so we start here and go to 3. and we will actually find ourselves at the same place, which is 2. So that means the limit of this function does exist and is 2. Now for letter D, it says here that the limit is none. The limit does not exist. So if we try to prove that, so first we have to find negative 2, which again is here. So from the left, we have at negative 1. From the left to negative 2, we have negative 1. Now, from the right, we have to find a graph or a line that comes from the right to negative 2, which is this line or this graph. So from the right, it goes to negative 2, which lands on positive 4. Notice that we have different one-sided limits. That means the limit of this function does not exist. Now, lastly, for uh, letter E, the limit of f of x as x approaches to 4. So again, find our C, which is 4. So 4. And notice that it is not a one-sided limit or one-sided limit. That means we have to find both from the left and from the right. So first, from the left, going to positive 4. From the left, going to positive 4, we actually end up at positive 1. Now, from the right to positive 4, we will end up at negative 4. So again, the one-sided limits are not equal. That can only mean that the limit does not exist. And that's all for this lesson. I hope you learned something and good luck. Good morning, good afternoon, and good evening. This video will discuss the lesson 2 of STM 112, continuity of a function. To begin, continuity is the rigorous formulation of the intuitive concept of a function that varies with no abrupt breaks or jumps. A sufficient understanding of continuity will simply be if you can trace any part of a graph without any stops or cuts while still considering the definition of a function. There are 3 conditions of continuity at the point. A function f of x is said to be continuous at x equals to c if the following 3 conditions are satisfied. The function value of c exists, the limit of f of x as x approaches to c exists, and the function value of c equals to the limit. Otherwise, the function is discontinuous. A function f is said to be continuous from the left at x equals to c if the function value of c is equal to the limit of f of x as x approaches to c from the left. And then a function f is said to be continuous from the right at x equals to c if the function value of c is equal to the limit of f of x as x approaches to c from the right. Polynomial functions are continuous everywhere. The absolute values of function f of x is equal to the absolute value of x is continuous everywhere. Rational functions are continuous on their respective domains. The square root of function f of x equal to the square root of x is continuous on closed interval 0 to infinity, to positive infinity. A function is said to be continuous everywhere if f is continuous at every real number. In this case, we also say f is continuous on R. On open intervals a to b, if f is continuous at every point x in between a and b, but not including a and b, just whatever values in between them. On closed interval a to open interval b, if f is continuous on open intervals a to b and from the right at a, so from the right of a. On open interval a to close interval b, if f is continuous on open intervals a and from the left at b. On closed intervals a to b, if f is continuous on open interval a to close interval b and on closed interval a to open interval b. On open interval a to positive infinity, if f is continuous at all x is greater than a. On closed interval a to positive infinity, if f is continuous on open interval a to positive infinity and from the right at a. On negative infinity to open interval b, if f is continuous at all a is less than b. On negative infinity to closed interval b, if f is continuous at negative infinity to open interval b and from the left at b. Let's move on to the different types of discontinuities. First is the removable discontinuity. A function f of x is said to have a removable discontinuity at x equals to c if the limit of f of x as x approaches to c exists, and then either the function value of c does not exist or f of c is not equal to the limit. It is said to be removable because the discontinuity may be removed by redefining f of c so that it will be equal to the limit. In other words, a removable discontinuity is remedied by the redefinition. Let the function value of c equal to the limit. Next, essential discontinuity. A function f of x is said to have an essential discontinuity at x equals to c if the limit of f of x as x approaches to c does not exist. So for the first case, if for a function f of x, the limit of f of x as x approaches to c does not exist because the limits from the left and right of x equals to c both exist but are not equal. So the one-sided limits of the limit of f of x are not equal. So if this is the case, then f is said to have a jump essential discontinuity at x equals to c. So again, if the limit does not exist because though both one-sided limits exist, they are not equal. Next, if for a function f of x, the limit of f of x as x approaches to c does not exist because either the limit of f of x as x approaches to c from the left is equal to positive infinity, the limit of f of x as x approaches to c from the right is equal to positive infinity, the limit of f of x as x approaches to c from the left is equal to negative infinity, and lastly, the limit of f of x as x approaches to c from the right is equal to negative infinity. Then f of x is said to have an infinite essential discontinuity at x equals to c. So basically, if the one-sided limits are infinite or infinity, then they are infinite essential discontinuity. So this is the summary to determine whether the function is continuous, removable, infinite essential, or jump essential. So first we have to ask whether the limit of f of x as x approaches to c exists. So if it does, if it's a yes, then let's proceed to ask if the limit is equal to the function value of c. Then if it is equal, then it is continuous. For the removable discontinuity, the limit of f of x as x approaches to c exists, but it is not equal to the function value. And then for the infinite essential discontinuity, the limit does not exist, and the one-sided limits also does not exist or do not exist, since they are infinity or infinite. And then lastly, for the jump essential, the limit does not exist, and the one-sided limits exist but are unequal. So let's begin with the guided practices. We are simply going to determine if the function is continuous or discontinuous at x. So first, the f of x is equal to negative x squared over 2x plus 4 at x equals to 2, x equals to 4, and x equals to negative 2. So first, let's get x equals to 2. So the first thing we have to do is to find the function value. So we simply have to replace x with 2 and then compute. Then eventually we will get negative 1/2 or negative 0.5. And then now let's proceed to getting the one-sided limits to determine if this function at x equals to 2 does have a limit or not. So first, let's start with the one that's from the left. So basically, we just replace the values and we'll get negative 1 over 2 or negative 0.5. Now, for the one that's from the right, again, just replace the values and we could see that the function value and the limit are the same. So therefore, f of x is continuous at x equals to 2. Next, x equals to 4. So again, let's find the function value of 4 or f of c. So let's use 4, then replace the values of x, and then compute. So 4 squared over 2 times 4 plus 4. That will give us negative 4 over 3 or negative 1.3333333. So next, the limits. First, that's the one that's from the left. Again, simply replace the value and then we will get negative 4 over 3. And then for the right, we also get negative 4 over 3. So once again, we could see that they are all equal. So that means f of x is continuous at x equals to 4. Now, lastly, for x equals to negative 2. So let's start with the function value. And if we replace the values of x with negative 2, we'll get an undefined answer since there's a 0 in the denominator. So just from here, we could already say that the function is discontinuous at x equals to negative 2. So let's proceed to finding the limits. So if we just try to replace x with negative 2, we'll just get an undefined. So in order for us to find the limit, let's try to get the closest value from the left to 2. So that would be negative 2.00000001. This could be any value, by the way, as long as it approaches to negative 2 from the left. So if we replace the values of x with 2.00000001, we find that it actually approaches to infinity, to positive infinity. So next, let's try to find the limit from the right. So the closest value to 2 from the right is negative 1.9999999. So that's the value that we will replace x. And if we do that, we find that the values approach or increases to, decreases to negative infinity. So since we have infinities for the limits, therefore, f of x is discontinuous at x equals to negative 2, and it has infinite essential discontinuity. So if we would graph the function and pinpoint x equals to 2, so 1, 2, we find that it is actually part of the graph, or the graph touches it. The same goes for x equals to 4, 1, 2, 3, 4. But when we try to pinpoint x equals to negative 2, 1, 2, we find that the graph approaches to negative 2, but it will never touch, since x equals to negative 2 is our vertical asymptote. For the next function, g of x is equal to x plus 1 over x squared minus x minus 2. And let's try to determine if it is continuous or not at x equals to negative 1. So again, let's find the function value and replace x with negative 1. If we do that, we'll end up with 0 over 0, which is indeterminate or simply does not exist. So this function is already discontinuous. Now let's proceed to finding the limit. Again, if we will try to simply replace the value of x to negative 1, we'll just get the same answer as indeterminate. So first, when dealing with this kind of function, let's factor out x squared minus x minus 2. And if we do that, we'll get x plus 1 times x minus 2. From there, we could cancel out x plus 1. And we are left with 1 over x minus 2. That means now we are trying to find the limit of 1 over x minus 2 as x approaches to -1 from the left. So here, we can now replace the values of x with -1. So 1 over -1 minus 2, that will give us -1 over 3. And then let's proceed with the one that's from the right. And we'll actually get the same limit or answer, which is -1 over 3. So since the function value does not exist, but the one-sided limits do exist and they are equal, then the g of x is discontinuous at x equals to -1. And it has a removable discontinuity. Again, why is it removable discontinuity? Because we have the limit, but we don't have the function value. So moving on, in order for this continuity to be continuous, we have to redefine the function. And to do that, we simply have to make a piecewise function that states that if x is equal to -1, then it is -1 over 3. By doing that, we are filling the hole in the graph. So before we redefined the function, we could see that at x equals to -1, there's a hole around negative 0.333 or -1.3. But after we redefined, we stated that if x is -1, then the answer is -1 over 3. We now have a continuous graph or function. Moving on, h of x is equal to the piecewise function 3x minus 2 if x is less than 3, x minus 1 if x is greater than or equal to 3. So first, let's try to get the function value. So simply get the value of 3 and replace it with x to get 2. By the way, we used x minus 1 because 3, according to the piecewise function, if x is greater than or equal to 3. If x is greater than or equal to 3, we use x minus 1. So we will get 2. Now let's proceed with the limits. First, the limit of h of x as x approaches to 3 from the left. So we will use 3x minus 2. Since from the left, meaning it has a lower value than 3. So if x is less than 3, we will use 3x minus 2. From there, we simply replace the values of x with 3 and we'll get 7. Next, from the right, now this time we'll use x minus 1 since we'll have to use a value that's greater than 3. And it will give us 2. 3 minus 1, that's simply 2. Now, we may notice that the function value and the limits are all not equal. So that means h of x is discontinuous at x equals to 3, and it has a jump essential discontinuity Again, because the function value and the limits are not equal, though they exist. If we graph it, it would look something like this. And you could see that at x equals to 3, 1, 2, and 3, there's actually a jump or a gap in the graph. Now, next, j of x equals to the piecewise function square root of x minus 1 if x is greater than 1, 3 if x is equal to 1, 4 minus x squared if x is less than 1. And we'll try to find out if the function is continuous or discontinuous at these intervals. So first, open intervals 1 to 4. So since we are going to find any value using, we are going to use any value in between 1 and 4. So not including 1 because it's in a open interval, and not including 4 because it is also open interval. So that means 2 and 3. So since 2 and 3 are greater than 1, we will use the square root of x minus 1. So if we try to replace the value, we would always get a answer. We don't get an undefined answer or an invalid answer. So that means this is actually continuous on the open intervals 1 to 4. Again, the reason behind that is whatever value that we use, which in this case, we can only use 2 and 3, we will always have an answer. So that means there are no gaps or holes in the graph. Next, for the closed interval 1 to open interval 3. So let's try to get the limit of the square root of x minus 1 as x approaches to 1 from the right. So here, we are no longer trying to find, you don't need to find the limit from the left, since we will start at 1. We will not go lower than 1. We'll start exactly at 1 and then move on to positive 3. So just simply get the limit from the left. And we are going to use x, the square root of x minus 1, because since it's from the right, so that's greater than 1. So based from the piecewise function, if x is greater than 1, then we'll use this square root of x minus 1. So from there, just replace the value. So x becomes 1. 1 minus 1, that is 0. The square root of 0 is still 0. Now next, we'll try to get the function value of 3. I mean, the function value of 1. And it says here that if x is 1, then it is 3. So just from here, we can already say that they are not equal. The limit and the function value is not equal or are not equal. So therefore, it is discontinuous on closed interval 1 to open interval 3. We no longer need to find the limit and function value of 3, since just from doing that to the 1, to our 1 here, we can already say or conclude that the function is discontinuous. And that's it for this video. I hope you learned something, and thank you for listening.